Hello everyone, welcome back. In this lecture, we shall see fundamentals of convection heat transfer with primary focus on forced convection with related equations. Convection heat transfer. As we know, the rate of convection heat transfer between solid surface and moving fluid is given by Q is equal to H into A into Ts minus T infinity, where H is the convective heat transfer coefficient and Q is the convective heat transfer rate. This we have seen in the previous lecture. Okay. So here if you see in this image, heat conduction happens in the solid block, and from the solid surface to the fluid, the heat is transferred through convection mode. We can see here. Okay. Next we shall see about convective heat transfer coefficient H value. So what determines the H value? The convection coefficient H depends on fluid properties like viscosity, thermal conductivity and specific heat, and also flow velocity and the regime in which flow is operating, that is laminar or turbulent flow, the geometry in surface roughness, and also temperature differences. So how to calculate the H value? There is no universal formula for H. We have to use empirical correlations using non-dimensional numbers like Reynolds number, Prandtl number and Nusselt number for forced convection. In case of free convection, there are two other numbers like Grashof number and Rayleigh number. But for this case, we will stick to forced convection and we will see about these three non-dimensional numbers. Next we shall see the non-dimensional numbers. The first one is Reynolds number. As we know, Reynolds number is a dimensionless quantity that helps to predict the flow regime, whether it is laminar or turbulent in a fluid. It also quantifies the relative importance of inertial forces to viscous forces in fluid flow. The formula is given as Reynolds number is equal to rho into U into L divided by mu, where rho is the fluid density, U is the characteristic velocity of the fluid, L is the characteristic length, and mu is the dynamic viscosity of the fluid. The unit is Pascal second. So in case of flat pipe, the characteristic length is given by the length from the leading edge, and if it is in case of pipe, the characteristic length will be the diameter of the pipe. So this is the formula for Reynolds number. It is nothing but ratio of inertial forces to viscous forces. Let us see the significance and physical importance. Okay. If the Reynolds number is low, it means the flow is laminar. That is, the flow moves in smooth layers and viscous forces dominate, as shown here. If the Reynolds number is high, it means the flow is turbulent and the fluid moves with chaotic fluid motion and inertial forces dominate. The turbulent flow is given here. And if the Reynolds number is in the intermediate zone, then it is called transitional flow. The flow may transition from laminar to turbulent or vice versa depending on the disturbances. Let us see the Reynolds number limits for flat plate and pipe flow. So in case of flat plate, for laminar flow, the Reynolds number should be less than 5 into 10 power 5. And for transitional zone, it is 5 into 10 power 5 to 10 power 6. If it is greater than 10 power 6, then the flow is turbulent. In case of pipe flow, if the Reynolds number is less than 2300, then it is laminar. Between 2300 to 4000 is transition, and above 4000 is turbulent. Okay. Next, we shall see Prandtl number. This represents the ratio of momentum diffusivity to thermal diffusivity in a fluid. It means it is the ratio of viscous effects to conduction effects or thermal diffusivity. Okay. It reflects how well the fluid can conduct heat relative to how well it can flow. It also compares the relative thickness of momentum and thermal boundary layers in the fluid. We will not go in depth beyond this. We will see the formula and understand the significance. Prandtl number is given by momentum diffusivity divided by thermal diffusivity. Here momentum diffusivity is equal to nu, which is called the kinematic viscosity, which again is equal to mu by rho, that is dynamic viscosity divided by rho. And in the denominator, thermal diffusivity is given by K divided by rho Cp. K is the thermal conductivity, rho is the density of the fluid, and Cp is the specific heat at constant pressure. Finally, Prandtl number is equated to mu Cp by K of the fluid. These three are fluid properties. Okay, these properties vary with respect to temperature. So, at different temperature levels, we can find out the Prandtl number. It effectively gives the meaning of viscous effects to conduction effects. So, in the numerator, you can see the viscous term, that is mu, and in the denominator, we have got the conduction effects, that is thermal conductivity K. Okay. Here we can see the parameters and its units. Okay. So effectively, if we see, if the specific heat increases and if the viscosity increases, then the Prandtl number will increase. So it means the viscous effect will be dominating the flow. If thermal conductivity decreases, then Prandtl number will further go up. So it means if the thermal conductivity increases, then the Prandtl number will come down. That is, the denominator term will be high. So in simpler terms, for example, for liquid metal flow, the Prandtl number will be in the range of 0.01 to 0.001 because for liquid metals, the viscosity will be low and the thermal conductivity will be high. So the denominator will be high, therefore the Prandtl number will be in the range of 0.01 to 0.001. And in the case of engine oil flow, the viscosity will be high for oil and the thermal conductivity will be less. So in that case, the Prandtl number will be equal to 100 to 1000. This will be high Prandtl number zone. Okay. So effectively, Prandtl number represents the viscous effects to conduction effects. Okay. Next we shall see Nusselt number. This is an important number in terms of forced convection. We will see. Nusselt number represents the ratio of convective to conductive heat transfer at a boundary in a fluid. Here the convection includes both advection, that is bulk fluid motion, and diffusion, that is equivalent to conduction in a fluid. Okay. So the Nusselt number is given by total convective heat transfer rate divided by conductive heat transfer rate. So the total conductive heat transfer rate is equal to the effect of advection plus conduction, and the conductive heat transfer rate is given by conduction here. So the numerator is convective term H and the denominator is conduction term K. So to non-dimensionalists, we can divide by the characteristic length L. So effectively, Nusselt number will be equal to H into L by K. So Nusselt number represents the ratio of convection to conduction. So in case if Nusselt number is equal to 1, it means here the advection, that is the bulk fluid motion, will be equal to 0. Therefore, it will be conduction on top and bottom. So Nusselt number will be equal to 1. So it means the heat transfer happens only through pure conduction. So if the Nusselt number is in the range of 1 to 10, then the heat transfer is in the laminar flow or the slug flow. It means convection has just started. If the Nusselt number is high in the range of 100 to 1000, then it is a heat transfer in typical turbulent flow. Higher the Nusselt number, higher is the effective heat transfer rate due to convection. Okay, that is, the larger the Nusselt number, the more effective the convection heat transfer is. Okay, now we have seen the three non-dimensional numbers, Reynolds number, Prandtl number and Nusselt number. Now we shall see, using these three numbers, how to find out the conductive heat transfer coefficient. Now we shall see the empirical correlation for heat transfer coefficient in the case of forced convection over a flat plate. The Nusselt number at any location on a flat plate is given by Nu is a function of Reynolds number and Prandtl number. For laminar flow, the Nusselt number at any location x is equal to 0.332 into Reynolds number power 1 by 2 into Prandtl number power 1 by 3. And in case of turbulent flow, it is given as Nusselt number is equal to 0.0296 Reynolds number power 4 by 5 into Prandtl number power 1 by 3. So this represents the Nusselt number at any point on the flat plate. Okay, if you want to find out the average Nusselt number, then it is given as the average Nusselt number is equal to 1 by L into integral 0 to L Nusselt number at x into dx. So it is also given as average Nusselt number, which is equal to HL by K. H is the average convective heat transfer coefficient on a flat plate, L is the characteristic length, and K is the thermal conductivity. So this is the formula for average Nusselt number. Next, coming to summary, to find out the net heat transfer rate through convection, you need to know the H value. So to find out H, we need to know the Nusselt number. To find out Nusselt number, we need to know Reynolds number and Prandtl number. The formula is given here. For Q, it is equal to H into A into Ts minus T infinity. H is equal to Nusselt number into K by L. Nusselt number is given by the empirical relations, which is a function of Reynolds number and Prandtl number. And we know the formula for Reynolds number and Prandtl number. Okay. So based on this, we can find out the convection heat transfer coefficient and also the net heat transfer rate. Okay. Finally, convection is critical in fluid-based thermal systems, and forced convection is more predictable and efficient than natural convection. The governing equations plus empirical correlations give us the value of H. Okay. In the next lecture, let us simulate a simple forced convection case in a flat plate using Ansys CFX. Thanks for watching the video. I will see you in the next lecture.